So let's get started, guys. So we will talk about Newton's laws of motion in this chapter. Okay. Now, so far what we had been talking about, the subject was kinematics. Kinematics just involved the description of motion. All that involved was giving the position as a function of time, and from that you calculated velocity. Okay. So we learned that this was true, and then we learned that this was true. Acceleration was defined as dv by dt. Okay, so this subject was called kinematics. It was just about describing a motion. Okay. Now what we'll learn is what causes motion and what causes changes in motion. Okay, and so that is called dynamics. And at the heart of it is Newton's second law that you'll learn. To get an acceleration, that is to get a change in motion. Okay. So if you're at rest, to start moving, you have to accelerate. To accelerate, you have to apply a force. Okay. And that's what we're going to learn. So we'll learn the three laws of Newton's motion, Newton's three laws of motions. Okay. What's that?
Oh, that's rocket picture.
Oh, yeah. Gotta have rockets. So we'll learn all these topics. So Newton lived roughly about 75 years, back about 350 years ago. He was pretty smart. He discovered the law of gravity, gave us the laws of motion. He invented calculus. And he also made great contributions in theory of light and color. Okay. Had he made contributions in any one of those fields, we would have been talking about him. But he contributed in all those fields. Okay, the first law says if an object is moving and there is no force acting on it, it'll maintain its velocity. Okay. So for instance, but I mean, this is not observed easily in everyday life. So for instance, here's an object, I push it and it came to rest. Why did it stop? Friction. Okay. So how did they come to the conclusion that if no forces act on it, it'll keep moving forever? Have you ever seen anything that keeps moving forever? No. Okay, so this law was actually discovered by Galileo. So what he did was he progressively decreased friction, and the object would travel further and further. Okay, and then from that he concluded that if he could remove friction completely, the object would move forever. Okay. All right, so Newton's first law states that when no net force acts on an object, its velocity is constant and its acceleration is zero. So the closest we come is an air hockey table. Actually, there are other places. An air hockey table, the idea is this is one way to reduce friction. You blow, so this puck is traveling on a layer of air and the friction is very low. And it will travel . Oh yeah, so you guys have all played air hockey. All right, we won't play air hockey, but you guys, so go watch an air hockey video. Why isn't it loading? Why isn't it playing? see the velocity is constant between collisions. So I don't know, maybe if you had an air hockey table from here to Palm Coast, it would probably make it. So that's Newton's first law. So here's Newton's second law. So what happens if you apply a force? If you apply a force, Mr. Newton said that you would have an acceleration. And what Mr. Newton realized was the acceleration is proportional to the force. You double the force, your acceleration would double. And for a given force, the greater the mass, smaller the acceleration. Okay. Now from here, you can also understand why this is called Newton's first law, because this law was actually discovered by Mr. Galileo. So why do we call it Newton's first law? You can see that all Mr. Galileo discovered was if the net force is zero, acceleration is zero. So it's a special case of the second law. Yep. Now here's an interesting thing. So we've learned several things about it. Okay, so let's look at it from a mathematical equation. Okay, what you have, a force is a vector, so you'd better have a vector on the right hand side, and the acceleration is a vector. So this is a mass times acceleration, a scalar times a vector, and that's a vector. Okay, and here's another interesting fact about this. How many equations is this? 3 equations. Okay, so when you have vectors, and if these are 3-dimensional vectors, 2 vectors are equal only when their corresponding components are equal. The x component of the force is equal to mass times x component of the acceleration. Fy equal to mfay, and so on. Now here's the interesting thing about this. So if you apply a force in the x direction, all you can do is affect motion along the x-axis. A force applied in the x direction cannot influence these two guys. Yep. So that's why motion along orthogonal directions are independent of each other. Yep. You apply a force there, all you can do is affect that. All right, again, units for this are mass, meters per second square, and that combination of unit is called a Newton in honor of Mr. Newton. Yeah. So these are some of the old units. Mass was in slugs, acceleration in feet per second square, and then the force is in pounds. Okay. Okay, Newton's third law states the following. Okay, by the way, forces always come in pairs. Okay, there's not a single force. So when forces are between objects interacting, okay, so when this lady pushes on the wall, she's exerting a force on the wall. And what Mr. Newton realized was the wall exerts an equal and opposite force on the lady. Okay, so if you push something with a force of 10 pounds, that object pushes you back with a force of 10 pounds. Okay, you might not, so you probably all done this, but maybe not realize it. When you hammer a nail, okay, the nail goes in, but remember the hammer was coming at speed and stopped. What stopped the hammer? The opposite force. Okay? So Newton's third law says for every action there's an equal and opposite reaction. Mass is the amount of stuff in an object. Okay. The weight of the object is the force with which a planet or a large body pulls you. Okay. So the force with which a body pulls you will depend on the body. Okay. Your mass will not depend on the object. Okay. So when you go on the moon, your weight, you're 1/6 as heavy as on Earth, but your mass is the same. So here's an interesting point. So on this lady, there are two forces acting. This lady is pushing and this lady is pushing. Okay. And she'll move in a certain direction. Okay. Now there's that force and there's this force. Okay. The sum of these two forces are that force. That's the net force. Okay. Okay, so now we'll consider two cases. We'll apply these two forces on her and just this one single force on her. Okay. If you just look at her motion, you can't tell if two forces are acting on her or that one net force is acting on her. Okay. So from the motion will be identical and you can't tell the difference. Okay. So that's the superposition principle. The effect of the net force is the same as the sum is the same as all the other forces acting on it, okay, which gave you the net force. When several forces act on a body, the effect is the same as that of a single resultant force. So the gravitational force on you, the magnitude of the gravitational force is your weight. Okay, so let's say you're on a planet, and this planet, Mr. Newton gave us this law of gravity. Mr. Newton said every object in the universe attracts every other object in the universe. Okay? So this planet will attract you. Okay? And by the way, Mr. Newton gave us a formula for the magnitude of this force. The magnitude of this force is G times the product of their masses divided by the distance squared. M1, M2. R is the distance. R is the distance between the center of mass of this object and the center of mass of that object. Okay. Divided by that. Okay. So this is the Newton's law of gravity. Okay, so this object is attracting that object with a force. The force is directed toward the center of the object, and that's the gravitational force. The magnitude of this force is your weight. Okay. So your weight will depend on what planet you are on. Your mass is independent of where you are. Okay. All right, so here's an object. Yeah. So here's gravity pulling it down. And of course, this is not going through his hand because his hand is pushing with an equal and opposite force. And since this guy is not moving, this force must be equal to that force. Okay? So whenever you place an object, what happens is this object compresses the atoms there, and those atoms push back. Okay? So it deforms the surface, and those atoms push back. Okay? And that's called the normal force. It's called normal because it's always perpendicular to the surfaces that are in contact. And that's why it's called the normal force. Okay? And right now, the normal force is equal to the weight of the object. What is the normal force right now on this guy? It's equal to the weight of the object. What is the normal force now? It's greater. It's weight plus the force with which I'm pushing. Okay? The reason this is important is the friction force will depend on the normal force. Okay, so for instance, so the friction force will depend on the normal force. The friction force now is greater. Okay? Okay. Why does the friction force depend on the normal force? Now, if I press down on it, there are more atoms sticking together, okay, that are holding it back and pulling it back. Okay. So that's the normal force. So objects on an incline. Okay. So you want to make sure you understand this. Okay. We'll use this quite a bit, I guess. So here's an object, and again we will keep things simple. We'll represent the object by a point. Gravity pulls him straight down. That's the angle of the incline. Okay, so gravity pulls him straight down. What you're interested in is, see, there's the force of gravity, but this is not useful. What is more useful is this component of the gravity and this component of gravity. Okay. So we'll write it down. We'll figure it out once for all, and then you'll just remember it. Okay, so this is a right angle triangle. This angle is 90 degrees, so this angle is 90 minus theta. Okay, so this, and then we'll complete this triangle. Okay, so this angle is 90 minus theta. This component is mg cosine 90 minus theta, which is equal to mg sine theta. And this component is mg sine 90 minus theta. This component is mg sine 90 minus theta, which is equal to mg cosine theta. All right, so again, I will draw another diagram here. An incline is defined by this angle. The weight of a person on, so this component of his weight is mg sine theta, and this component of his weight is mg cosine theta. Okay, so you just commit that to memory. So if you were skiing and there was no friction force, if there was no friction force, your acceleration would be g sine theta. Okay, that's the force acting on you divided by your mass will give you acceleration. So for an object sliding down an incline, a frictionless incline, the acceleration is g sine theta. Okay. We'll deal with a lot of ropes, okay, under tension. So the best way to think of them is a good way to think of them is think of a stretched rubber band. Okay, so you hold on to a rubber band and stretch it. Okay, so I have, what is this rubber band doing to this? It's pulling. What is the rubber band doing to this hand? Pulling. Okay. So rope under tension is pulling both objects. Okay. What direction is it pulling? The rope just wants to get shorter. So it's pulling this object and the rope is pulling this object. Yeah. Now with the rope you can't push, you can only pull. Okay. So what does this tension mean? Okay, so let's say, so again, I'm going back to my rubber band. I've stretched this rubber band, and let's say the rubber band is under a tension of 20 pounds. What does that mean? This rope is pulling this hand with a force of 20 pounds. It's pulling this hand with a force of 20 pounds. That's what that means. Yeah. All right, we'll deal with a lot of this. So this object will be under a tension. The rope is under a tension, and so it's pulling this object with a force of magnitude T. And this. All right, now in this diagram, see, they show you the tension in this rope is the same on this side and on this side. What that assumes is that the mass of the pulley is negligible and it's frictionless. Okay, later on you will do so in your junior level you'll do a statics course when the mass won't be negligible for the pulley, and when the mass is not negligible, the tensions on either side will be different. Okay, so right now we'll keep things simple, and soon as you see that the tension is the same on either side, that means that the mass is negligible. Okay, so that's what's implied. Okay, so here's a bridge. It was built in 1937. It's a suspension bridge. All right, let me show you an old style bridge. So here's an old style bridge. And here's a new style bridge. What is the advantage? What are the... I'm sorry? So, you can see that the suspension bridge takes a lot less material. Okay, and to have a big ship pass underneath that, this bridge would have to be a lot more in the. Okay. Even though this might be stronger, absolutely it might be stronger, but pound for pound, this guy's stronger. Okay, so for instance, I'll give you an example. This was, you guys know the World Trade Centers. The Empire State Building, for every 100 pounds used in the Empire State Building, the World Trade Center used only about 30 pounds. Yeah, so that much improvement. Well, what is the price you paid? The World Trade Center would sway. I guess so. You had to get around that problem. You had to make sure that the windows didn't pop and stuff like that. Okay. The Burj Khalifa, the top floor, sways about 2 meters. And that's the top floor is the most expensive floor. You got to sell that, and that guy he can't get sick. Remember, guy or gal can't sick. I mean, if they get sick while they're drinking their coffee, they're not going to pay you $50 million for that flat. Yeah, so you have to worry about all of that. All right, so you're using less material, but you have other problems. So how do you solve problems like this? Okay, so we'll come to this in a second. Okay, well, actually, let's talk about it now. Okay, what you'll learn in one of the later chapters. Okay, so let's start off by doing this. Okay, so I have two identical columns, and I want to break them. Okay. And what I'm testing the strength of these columns. I'm going to apply a force like that. Now, if I just apply that force, it'll just move in that direction. So what I have to do to break it, I have to apply an equal and opposite force like that. If I push it like that, it'll just move in this direction. So I got it. Okay. Which way will it break first? This way or this way? Okay. So it turns out that most materials are stronger under compressive forces. So if you had a concrete column, this is 10 times stronger than this. So if 100 pound would break this way, you need 10,000 pounds of compressive force. All right, so once you learn that, now, so what goes into your design? If you have, by the way, can you stop doing that? Your leg. It's distracting. So, if you have any structure and you want large forces, you'd better have that large forces compressor. So let's see how that went into this design. All right. Right, so let's say the bridge is full of traffic and you have 1,000,000 pounds to lift. Yep. So now we'll do a diagram. So this bridge is suspended by these cables. Let's say there's 1,000 cables. And so each cable is lifting how much? 1,000 pounds. Yeah. So this cable is, remember, this is under tension. This is pulling this cable. And so this cable is pulling that cable down with a force of 1,000 pounds. All those guys are pulling down. So they're pulling this cable down. They're pulling this cable down. And these forces make that a compressive force. And the ground is exerting a force on that guy. Each of these cables is bearing only 1,000 pounds. That's a tensile force. It's a stretching force. So 1,000 pounds, you don't have to break that cable. But here's a compressive force. How much is that compressive force? I'm sorry? Very good. 500,000 pounds. This guy's bearing 500,000 pounds. This guy's bearing 500,000 pounds. Okay. So the large force is a compressive force. Okay. So that's what went into the structure. Yeah. Here's another example of this. Okay. So what is the shape of that dam? See the dam, so here's the walls of the dam, there's the walls of the canyon, and the dam is shaped like this. The water is pushing like that, and the walls are bearing a compressive force. Yeah. So again, once you learn the properties of material, that factors into your design of stuff. Okay. Here are some forces. Okay, so this shows you. Okay, that's the force that's needed to stretch a DNA molecule. There are these things called optical tweezers, and maybe we'll arrange a visit to one of the labs in UF. They have the optical tweezers, and they can measure the force that's needed to stretch a DNA molecule. Yeah. What is this thing? I'm sorry? What does this do? Very good. So we saw the tension is the same. Okay. When is the tension in the rope the same? When these masses are negligible. Anyway, so let's say you want to lift a 100-pound object. So here's the tension. So this tension is acting that way. So this rope is pulling this way up. This rope is pulling this way up. So you only had to pull with a 100-pound force to lift up a 50-pound force. Okay. So you only have to apply a 50-pound force to lift a 100-pound object. That's what a machine does. Okay, it's a force multiplier. It let you lift a 100-pound object with a 50-pound force. Sounds like free lunch to me. What gives? What gives? How come you're lift?
Is it because you're pulling it over a greater distance?
Very good. Okay, so when you want to lift this 1 feet, you have to pull the rope 2 feet. Okay, work is force times distance. Okay, so the output work is in a frictionless system. It's always going to be equal to input work. Okay, so if you apply a smaller force, you have to apply it over a larger distance. You're willing to do that because otherwise you wouldn't be able to lift this object. Okay? So that's what you want to do. Okay? And if you, of course, if you have friction in the system, then your input work is greater than your output work. Okay? So here's this. This is a simple machine, and the mechanical advantage of a machine is defined as the output force divided by the input force. So the mechanical advantage of this machine is 2. Okay. What that means is you can, with a given input force, you can lift twice the weight. Okay. So this is the same thing. So this pulley setup, the mechanical advantage is 2. You can lift a 100-pound object with a force of 50 pounds. So to calculate the mechanical advantage, all you have to do is count the number of strings attached to your load. Okay. For this, the mechanical advantage is 3. For a 100-pound object, you can lift it with a force of 33 pounds. What is the price you pay? For every feet you lift, you have to pull 3 feet. Yeah. This has a mechanical advantage of 4. All right. You always do cost-benefit analysis. After a while, the return. In real systems, there is always friction, so you're adding up friction. Friction is wasted money. So, but there might be situations when you have to lift a really heavy load, and you're willing to do that. All right, here's a mass attached to a spring. All right, so here's the equilibrium situation. Okay. Now, if you compress the spring, if you push on the mass this way, what does the spring do? It pushes back in that direction. It's pushing back where the system wants to come back to its equilibrium position. If you pull on the spring, the spring will pull you back. The force that the spring exerts is a restoring force. It's trying to restore the system to its equilibrium position. It's like this. If you have a marble in a valley, you disturb it, the gravitational force will want to bring it back. That's a restoring force. Okay. How about now? That's not a restoring force. Okay. You disturb it from that location, from that equilibrium location, it'll run away. Okay? So the spring is exerting a restoring force. And it turns out that the spring force, this is extremely important. We will spend an entire chapter on this. Okay, the spring force, the force that the spring exerts, is proportional to the displacement. Mr. Hooke discovered this, and it's known as Hooke's law. Yep. So if you double the stretch, the force will double. So it gets harder and harder to stretch more and more. This constant is called the spring constant. And it tells you how stiff the spring is. Stiffer the spring, larger K is. Okay? So here's an interesting system. Okay. Again, we'll assume that the pulleys are massless. What does that mean when you say the pulleys are massless? The tension is the same on either side of the pulley. Okay. Which way will the system move? If it does move. So it turns out that, okay, if M1 is greater than M2 plus M3, then it'll accelerate downwards. And if M2 plus M3, if M2 plus M3 is greater than M1, then it'll accelerate upward. And of course, if M2 plus M3 is equal to M1, it'll remain at rest. And if you get it moving, then it'll move at constant velocity. Okay. So here's an interesting application of this. Okay. So as long as M2 plus M3 is greater, this will move upward. Right? So here's a very interesting application. So here are 4 buckets. Fill them with sand. And as long as the buckets are heavier than this platform will go up. And you don't even have to nail these things. So in fact, these things are not attached. You put enough sand in there, and you can sit there as well, and that won't fall down. So your weight and the weight of the platform should be less than the weight of the sand in there. And you don't have to nail that thing. All right, so here's a final statement we'll do. We studied Newton's 3 laws. What are Newton's first law? Well, I'll state Newton's second law. Second law is force equal to mass times acceleration. And the first law is if the net force is 0, acceleration is 0. And the third law was, of course, action and reaction are equal and opposite. Okay. Newton's 3 laws apply in inertial frames of references. Okay, inertial frames of references are frames of references that are not accelerating. Okay, so any frame that is accelerating is a non-inertial frame of reference. And then Newton's laws don't apply. Okay, so what does Newton's law say? That if you're accelerating, there's a force acting on you. And if there's no force acting on you, then you're not accelerating. And that's what Newton's law says. Okay. So now let me show you a counterexample. Okay, so we're going to go to the North Pole and play hockey. Okay. And Wayne Gretzky is going to hit the puck hard. And what we'll do is we'll hover over the in a helicopter. Well, no. Anyway, we're out in space and hovering, so don't ask me how. Okay. And we watch the puck. What does the puck do? So actually, so the Earth is spinning away. This Earth is spinning, and the puck, no, so you're watching this standing here on Earth. So you're stuck to the Earth, and there was no friction, and the Earth spins from under the puck, and the puck goes away in that direction. You see, the puck is accelerating, and there was no force acting on the puck. And why did you see that? Because you were attached to the Earth, which was spinning, and that's a non-inertial frame. That's an accelerating frame. And so from a frame attached to the Earth, Newton's laws are not valid. You had a puck accelerating without any force acting on it. Okay. Now, to observe this, for you to observe the curvature, you have to observe this. I mean, it will be noticeable if the puck has been traveling for at least half an hour. Okay. So for me throwing this thing, the Earth has not rotated enough, so it's an inertial frame for small amounts of time. Okay. So if you're attached to the Earth is an accelerating frame, it's a non-inertial frame. Okay. So anyway, so you have to be aware of this fact. All right, that finishes this chapter.